Hello and welcome back. Differentiation under the integral sign. A fairly straightforward integral to do today. I forgot the dx by the way here. Okay, it's the integral from 0 to infinity. On the top we got two negative exponentials subtracted, e to the minus 2x minus e to the minus 8x, and I'm writing dx on the bottom. How shameful. Okay, over x. I don't know who wrote that by the way. So this is the integral we're going to do. Okay, this is how we're gonna attempt this one. First of all, notice that this particular integral has a problem, not so much as x goes to infinity, because of course that is actually will converge, it will just go to 0, and also this helps going into 0 as well, obviously, as this gets infinite, the 1 over x. But when x is equal to 0, this grows out of bound, the 1 over x. However, the top is going to 0 quicker because, of course, we're going to get obviously e to the 0 and e to the 0, 1 minus 1, faster than this, of course, diverges. We're not concerned about this at the moment because, of course, we have to assume that this particular integral, that's what the question says, converges. So we're going to see how we're going to attempt it. Okay, for differentiation under the integral sign, we're going to define an integral I of some parameter. I used A, I used K. Let's use T this time. So I of T. And what shall our parameter be? First of all, we're trying to somehow get rid of this x on the denominator. So we need to differentiate some parameter up here, so ax, bx, or something like this, tx as I put it up there. So do we call t the 2 or the 8 in this particular case? The answer is it doesn't really matter. I'm going to do it with t is equal to 2. As an exercise, you can try after you see what I'm going to do with this particular integral, try to put your t here and you will get exactly the same answer. So my I of t is e to the minus tx, so t now stands for my 2 in there for the time being, e to the minus 8x. Actually, it doesn't stand for my t doesn't stand for my 2. I'm going to replace it, and when I want to find my integral, I will replace my t with 2. So here we go, over x dx. Okay, now we're going to differentiate both sides of this particular integral with respect to t. So di by dt is going to be d by dt 0 to infinity. I'm going to split this particular integral, the integrand rather, because it's going to be easier for my next step for everybody to see. E to the minus 8x over x dx. And now by Leibniz rule, I'm going to commute the integration and the differentiation. At the moment, this is a function of one variable because once, of course, is integrated with respect to x, this is a function of t. However, when this goes inside, let's do it properly for once. We're going to have to use a partial derivative. So this now will become not to infinity, and we're going to have d by dt of e to the minus tx over x minus e to the minus 8x over x, close bracket, dx. Okay, is this differentiation difficult to do? Not at all. First of all, let us note that this is just a function of x, so when we differentiate it with respect to t, this will just vanish. There's nothing from this. However, let's write it here. Integral not to infinity. We're differentiating now this with respect to t. So the 1 over x is a constant. Let's write it outside. It makes no difference for this bit here. And if we differentiate with respect to t, now we're going to get a minus x coming to the front. Minus x, this is meant to be my bracket, minus x e to the minus tx, close bracket, dx. And this is the whole point that I chose to do that, is I was trying to get rid of this x on the denominator, which now has disappeared. So now, we have a nice expression. We have a very simple integral. Oops, not minus x, minus, where's my sponge? Okay, let's take that off. Minus, the x's will cancel, and we'll have e to the minus tx negative exponent dx. I'm not going to go and do this analytically with limits or anything like that. It should be fairly obvious. This will now integrate. Let's put square brackets. We're going to get e to the minus tx. Of course, the integrations with respect to x. And because we have a minus there, a minus 1 will go plus. So we're going to have 1 over t. And we're integrating in, the limits are in x. Let me just write them from x is equal to 1 to x is equal to infinity. And can we just see the board if I write here? So this will now evaluate when x goes to infinity. This will vanish because of the negative exponent. And remember, the t is chosen, so that's positive. I forgot to mention it. So here, I should have really written a condition where t is a positive parameter. So as x tends to infinity, we're going to get 0 minus, we're putting x is equal to 0, so this becomes 1. So minus 1 over t is what we've got so far. Okay, let's clear the board and let's see what we have actually achieved so far. So remember, all of this answer now, this final answer, we don't really need the 0 anymore, is not my I of t, but my di by dt. So let's wrap up to here. And let's put our answer there. And now we're practically at the end. We're very close to the final answer. So this is equal to minus 1 over t. So of course, I want my I of t. I got to solve a very simple differential equation. It's not even, we can call it if you want to make him feel better, a differential equation. It's just a simple integration really. So my I of t, if we integrate that, is going to be minus log t, and let's not forget the constant of integration plus c. So let's think now how we're going to evaluate this constant. We need to pick a suitable value for our t. Our I of t is up here. I'm going to rub off this and let's put it up there. Is equal to minus the log of t plus a constant. And of course, let's write it up here. T is in fact a positive number. That's why I didn't put mods in there. Okay, do I need these things? No, we can rub it off. All right, so we can evaluate this constant by picking a suitable value for my parameter to go in there. And what is now this suitable value for my parameter? What t can I put in there? If I put, for example, something to perhaps get rid of this log, maybe if t is equal to 1, unfortunately here I'll have problems because of course I don't know what this is. So the only suitable number that will work for this particular one is to actually say let t equal to 8, and the reason for that is because if you look at the numerator of the integrand there, it's going to be e to the minus 8x minus e to the minus 8x, so this in fact will be 0, so the integral will become essentially 0. Hope you can all see this particular step is equal to minus the log of 8 now plus c, so my constant of integration is in fact the log of 8. So I don't want to be rewriting all of this, so you'll allow me to write there minus log t plus the log of 8, which of course is the same as the log of 8 over t. So I am done because I was after finding this particular integral, and this particular integral is of course my I of 2. So about to write 8 there. I of 2, and the I of 2, 2 there, 2 there, and 2 there is equal to the log of 4. I hope you followed it, and I hope you're laughing like I am at the moment.